Hi friends, welcome back. We're going to discuss about edge betweenness centrality. The objective of edge betweenness centrality is basically to find out the edge which lies on most of the number of shortest paths between all pair of nodes. And this is very essential for community detection algorithms. These critical connections which fall on the majority of the pair of nodes, right, between the paths between the pair of the nodes, will have high edge betweenness centrality because they are connecting the nodes together, right? So it also talks about ultimately the edge's importance. In community detection algorithms, this is used. So let us try and understand how it is computed. From a mathematical standpoint, the formula stands as the edge betweenness centrality for a given edges, the total number of shortest paths between a pair of nodes, let's call this as SNT, divided by all the possible node of the shortest paths between those pair of nodes. So we will have to first look at two nodes, S and T. And then we will identify all the shortest paths that are possible between S and T in the network. And that becomes our denominator. But in the numerator, we will only consider those shortest paths which pass through the edge in question here. Right? So let us do this computation manually by considering a very, very simple network. So step number one, we need to have a network. And then we will have to analyze all the shortest paths between the node pairs. And then we will consider the edges which basically have or which appear in majority of these node pair connections. So let's talk, or let's stop talking and do the computation, right? So let's take a simple network. This is our network, a 5-node network. That means I will have 5 nodes. And in these 5 nodes, right, among these 5 nodes, you can see there are 1, 2, 3, 4, 5, 6 edges. So total edges that we can see in the network are 6. So if I now talk about the edge betweenness centrality, we are basically computing the value for these edges. But in order to do that, we need to look at the pairs. So if I have 5 nodes, then I would have 5C2 pairs. That means I will have in total 10 pairs. What are those pairs? AB, AC, AD, AE. This is with respect to node A. Then again, we will have BC, BD, and BE. Then from C, CD, CE, and finally DE. So these are the total pairs. Now we will try and look at the shortest paths which are passing through these nodes. Right? Let's look into the shortest paths. To start with, if I take AB, then we will have only one shortest path, right? That is AB itself. Then I will take AC. AC also I have only one shortest path. But if I talk about AD, then I can see two possible paths, one and then two. That is ABD, this is one path, ACD. So I have two paths which are possible between AD. Right? Next, we will talk about the next connection, which is AE. So again, AE, I can see only one shortest path. That is from A to C and C to E. Next, we'll move on to the pairs which start with B. So BC, we don't have a direct connection, but we can see connection between BC as BAD, BAC and BDE. We will consider only directed connection here. So I mean, when I say direction, we will not consider A because we have already considered the pairs here. We'll move downwards. So I'll only consider BDC. Okay, for a directional graph, you can say. So between BC, I have only one connection. So here one, but for this we have two connections. Here one, again here we have one connection. Then BD, of course, one connection. Then for BE, again there is only one connection. BE basically is this one, but we have to traverse this way. So one connection. And then CD, I see one connection directly. CE one connection, DE one connection. Right? So these are the connections that we are looking at between these pairs. So if I write them down, these are the connections. And only between A to D, I see two possible paths, which is ABD and ACD. Now what we do is we will try and see how many of these paths, shortest paths that we have analyzed here, are actually passing when we look into these edges. So we basically see how many, right? 6 edges are there. So we'll try and see how many of these edges are actually falling in this. Okay. So how do we do that connections? Let's first record the edges. That is AB, AC, BD, CD, CE, and DE. 6 possible edges that we can see in the diagram. Now let us see the shortest paths that this edge is actually appearing in. So when I say AB, it appears in 2 pairs, not 1 pair. Okay, first one is between AB, this pair, direct connection. Okay, this is the edge that we are talking about. But AB also appears in ABD connection. So I would say AD connection here, right? So this is the pair. So here it is appearing once. But when we talk about A to D connection, there are 2 possible paths. So this edge that we are talking about here will be appearing only in 50% of the paths that are existing between A to D. So I would only take 50% of the weightage from AD. If I have more paths, then obviously it will get distributed. Here 2 paths, so 50%. I don't see any other path, right? So let's move on to the next edge, which is AC. Now again, AC is appearing directly in a direct connection between AC. But again, it appears in the same path, A to D path. So I would say AD, but only 50%. But it also appears in AE path, right? So it also appears here, and there is only one path from A to E, which is ACE. So I'll take complete path weightage. Then between B and D, BD is appearing in directly, of course, BD connection. Then AD, I'll take 50% connection. But it is also existed, it's occurring in BC connection. BC connection. And it is also occurring in BE connection. So multiple paths are there here. Now moving on to CD, we have CD, this one, but we also have AD, which is 50%. Do I see in any other path? CD is in BC also. BCD. Right? Here you can see. Then CE, if I talk about, then of course CE direct connection and AE connection. And if I talk about DE, then we have direct connection D between D and E, and then BE also it is existing. BE, right? B to D, D to E. So these are the total number of shortest paths that this edge is lying in. Now we will have to count the weightage. So this is 1, this is 0.5 because it is only have 50%, right? Then AC1, ACD is again 50% between AD, and then AE is 1. This is 1, this is 0.5, this is 1, this is 1. 1.5, 1, 1, 1, 1, 1. So you get the weightages, which is equals to 1.5, 2.5, 3.5, so on and so forth. Fair, these are the values. Now, looking at this computation, we can clearly see that the pair BD has the highest weightage. So this pair becomes the most critical connection in this network, which has the high edge betweenness centrality value.